very good morning to Dr. Ayin. Today our group is going to make a short presentation on the group assignments of control system. Here are the members of this presentation, which include myself, Cho Kim Zeng, Wan Muhammad Izzadan bin Faizun, Muhammad Zuhilmi bin Muhammad Zuraidi. So in this presentation, we are proposing an industrial applications of field control DC servo motor, where the transfer functions of DC servo motor can be represented in this formula, where KT represents the tau constant of the loop, J represents the moment of inertia of the loop, B represents the damping coefficients of the loop, R represents the resistance of the loop, and L represents the inductance of the loop. So it is assumed that K equal to 10, J equal to 1, B equal to 2, R equal to 5, and L equal to 1. So the transfer function of Gx can be represented in 10 over x times x plus 2 and 5 plus x, where it is going to split into 3 parts with 1 over x as G1x, 10 over x plus 2 as G2x, and 1 over x plus 5 as G3x. And the calculations of the magnitude of G1x can be represented in this, which is negative 20 log omega. And the phase angle of G1x is always negative 90 degree between the interval of 0.01 until 100 radian per second. This table represented the magnitude in dB of G1x between 0.01 second and 100 radian per second. Next, we are moving to G2x, which is equal to 10 over x plus 2, where the magnitude of G2x can be calculated using the formula, which is 20 minus 20 log square root of omega square plus 2 square, where the table below represented the magnitude in dB of G2x within the radian per second of 0.01 and 100, where the phase angle of G2x can be represented and calculated in negative tangent omega per 2, where similar to G1x, omega is between the interval of 0.01 and 100. So the following table represents the phase angle based on the calculation above of G2x between 0.01 and 100. Last, which is G3x, which is 1 per x plus 5, and the magnitude of G3x in dB can be calculated using negative 20 log square root of omega square plus 5 square, where similar to G1 and G2x, so the magnitude of G3x can be calculated using the formula above, negative 20 log square root of omega square plus 5 square, and the table below represented the value in dB of magnitude of G3x between 0.01 and 100 radian per second. Similar to G2x, the phase angle of G3x can be calculated using negative tangent bracket omega per 5, where the omega is between 0.01 and 100 radian per second. The table below shows that the phase calculation of G3x between omega of 0.01 and 100. So that's all for my presentation. I will pass to my teammate for the next presentation.
Hi, my name is Wan Muhammad Izzadan, and I will continue our presentation regarding the total magnitude and phase angle of transfer function. So previously, we have divided our transfer function into 3 parts, which are G1, G2, and G3. So to calculate the total magnitude, we need to sum out the magnitude of each part of the transfer function. Okay, in the given radian frequency 0.01, the total magnitude are 40 decibel. At 0.1 radian per second, the total magnitude are 20 decibel, and at 1 radian per second, the total magnitude are 0, and at 10 radian per second, the total magnitude are negative 41, and lastly at 100 radian per second, the total magnitude are negative 100 decibel. So similarly as total magnitude, for total phase angle, we also need to sum up the phase angle of each part of the transfer function. So based on the previous calculation, we can obtain that at 0.01 radius per second, the phase angle are negative 90 degree. At 0.1 radius per second, it is negative 94 degree. At 1 radius per second, it is negative 128 degree. At 10 radius per second, it is negative 232 degree. At 100 radius per second, the phase are negative 266 degree. From the calculated previously, from the calculated total magnitude and total phase angle, we can sketch our body plot. So the body plot consists of two parts, which are magnitude part and the phase angle part. So from the calculated value above, we can finally sketch our body plot as above. Okay. As for the MATLAB simulation part, we need to make a little adjustment into our transfer function. The denominator of our transfer function need to be expanded so that we can input the values into the MATLAB. So as we expand the transfer function, we get our transfer function as above: 10 divided by s cubed plus 7s squared plus 10s. So by using the coding above, we can obtain our body plot and our gain margin and phase margin. So the gain margin, from the MATLAB, we get 16.9 decibel at 3.16 radius per second, while for the phase margin are 55.6 degree at 0.898 radius per second.
So continue with my turn. Okay, my name is Muhammad Zahimi bin Muhammad Radin, and my turn is to talk about body plot system stability. Okay, from the body diagram that we get, for the magnitude dB, we can get the gain margin, and for the phase degree, we can get the phase margin. Okay, as we can see that from the graph, the gain margin is located after the line of phase over frequency, and for the phase degree graph, the phase margin is located before gain crossover frequency. The comment from the graph that we can see is the value of gain margin is 16.9 dB, which is at 3.1 radian per second. Then the value of phase margin is 55.6 degree at 0.898 radian per second. As you can see that the graph is continue to fall down as the frequency increases. Most of the system can be defined as the stable system when gain and phase value are positive value. In addition, the greater the value of gain margin and phase margin can also be the factor to increase the stability of the system. So that's all from our group.